Okay, let's go ahead and get started. Hi, everyone. Good morning, good afternoon, good evening, wherever you're joining from in the world. My name is Yonatan Rabinovich. I'm the Global Marketing Manager at ASTERRA. Here with me today is Mark Hinton. Mark, say hi.
Hi, hello everybody.
Hi, great, we can hear you. Thank you all for joining. Some of you here might be familiar with ASTERRA or with our webinar series. Some of you might be joining for the first time. So if it's your first time here, welcome. We're glad to have you. I want to give a very brief introduction before we begin. Today's webinar is an introductory session for our EarthWorks soil moisture mapping solution. It's an opportunity to get the basics about the satellite technology that's behind what we're offering and how we apply it across different infrastructure verticals. Some of you might know us from the water utility industry, from our Recover product. So today we're talking about a different product that ASTERRA offers. And most importantly, it's also a chance to ask questions. This is an introductory session to the topic, so any and all questions will be welcome, and I'll address the Q&A session in just a minute. Okay, so just the schedule. I'll give my brief introduction now. Mark, who's here with us, will speak for around 40 minutes or so about EarthWorks. And then for the remainder of the hour, we'll have an open Q&A session. With regards to the Q&A, you should have access to do two different functions here in the webinar. One is the Q&A and one is the chat. Use the chat for anything that you want to pop in the middle of the presentation, maybe just a quick comment, or if you're not able to hear or you can't see the screen being shared or something like that. Any questions you have about the content of the webinar, please put them into the Q&A function. You're welcome to put the questions, and I encourage you to put the questions there at any time, but we'll only be addressing the questions at the end of Mark's presentation. So in the final portion of the hour, we'll be addressing all the questions that build up over the course of the presentation. And finally, about the recording will be available after the webinar for those who missed this, or for a colleague, or if you want to review something. It will be available on our website and on our YouTube channel. Briefly, before I pass over the baton to Mark, where you can meet ASTERRA for the remainder of 2024, tomorrow, Scandinavian Rail Optimization Conference in Stockholm. Mark will be attending. For those here from the rail industry. A bit later in the month, we'll be at the China International City Pipeline Expo happening in Wuhan, China. Then in December, the annual leakage conference in Birmingham in the UK. And finally, the American Waterworks Association Florida conference happening 8 to 12 December in Orlando. And with that, Mark, I'll pass it on to you.
Thanks, Johnny. And you'll drive the slides for me. Thank you. Okay, so hello everyone and welcome wherever you are in the world. My name is Mark Hinton. I'm the Business Development and Sales Director for ASTERRA as Johnny briefly alluded to there, for our EarthWorks product solution, and I have responsibility across the whole of the world except for the Americas. And I'm delighted to have the opportunity to speak with you today about satellite Earth observation, and specifically I'll focus here on what we know as L-band. Now, L-band is one of the bands within the SAR range of wavelengths. We'll come on to that a little in a moment. And ASTERRA are specialists in L-band. It's not the easiest area to work in, and we have unique capabilities. So SAR, for those that don't know, is short for synthetic aperture radar. ASTERRA has unique capabilities in turning that L-band data into conventional soil moisture measurements. And note, we're talking here about subsurface measurements, so looking beneath the surface. And a key motivation for me today here is to help educate, because the possibilities of Earth observation are that it increasingly provides to you, the engineering community, that connection to your own real world challenges. This is fast evolving, growing technology. And I personally am an engineer at heart. I'm a civil engineer and geotechnical engineering background. And really my day-to-day job is not to offer great deals of detail about the ins and outs of the space technology, but rather explain the data sets, the data insight that we've now got available to us that we can access through Earth observation, and how they line up to your engineering challenges. That's where I come from. That's what floats my boat and motivates me. So for examples, anomalies in soil moisture, they can be indicative of the potential for earthworks failures. So proactive monitoring for landslips, for example, or perhaps highlighting where drainage performance issues might be an issue. You might have blocked drains, that type of thing. So next slide, please. Okay, so there's some key points I'd like you to sort of take away here. So, and you can just reveal them steadily as we go here. So I hope after this short presentation that you'll leave with a better understanding of these points. Questions will be welcomed, as we said, at the end, or afterwards. Please reach out. Be happy to provide you with any further information. So during the presentation, just put those questions in, and I'll do my best to answer them when we get to the end. So first point, Earth observation is an available technology today. It's not so much about innovation, it's adoption, which requires often some cultural change and different ways of doing things than we've done traditionally. A lot of people, when they hear SAR, think of INSAR, but INSAR is not the only SAR. And I'll come on to that in a bit more detail. And L-band really matters because it has some distinct advantages, not least that it's able to see beneath the surface of the ground. So for your infrastructure challenges, wherever you've got earth and infrastructure, geotechnical assets, this is where L-band can play a role. And by looking at soil moisture, for those that maybe are geotechnical or geological type background engineers, you'll know soil moisture is a proactive way of predicting ongoing problems. If you get a landslip, an early indicator of that could be soil moisture. That will build up way before perhaps any discernible movement. So this is why it's proactive, and you can spot trends, spot anomalies. It's really important. And prior to now, it's been very difficult to do this on a large scale across large areas or extensive routes of transportation, road or rail. So seasonal changes are an indicative data point to monitor for climate change in your models. So improved EarthWorks asset deterioration models can be, those models can be improved using our types of data sets, and that can help you be more resilient in the way you plan for your assets going forward. So we're not offering a real-time monitoring solution here. It's typically more monthly or seasonal, but once you have that data, you can look at large areas very quickly in minutes from your desk and look, as it were, from space and triage, diagnose, really decide where you want to focus your follow-up. So this is all about providing you with the right decision assist tools to focus your resources. And this technology, this ability to detect subsurface underground soil moisture and map that, has applications, as you can imagine, across a wide variety of verticals, dams, levees, transportation, and so on. But it's the same underlying technology. And lastly, one more general point, Earth observation, and here specifically soil moisture, but Earth observation in general, it's increasing. There's generally not been possible before to measure these types of parameters across these large areas, and we've traditionally been limited to spot sampling or lab testing, that type of thing. So we have the ability now to provide a map GIS result across large areas quickly and efficiently. So as engineers, we need to start to make use of this perhaps newly available data set and insight, and really line those up to help us solve the known challenges we all day-to-day face into. Thank you. Next slide, please. Oh, we're already there. Sorry, apologies. Okay, so at ASTERRA, we actively measure our impact. We use the UN sustainability goals for reference. Very proud of our recent milestones, including passing 1 million megawatt hours of energy saved, 250,000 tons of CO2, 2 billion cubic meters of water, etc. Much of that has come from our sister product that we're not really focusing on today, but from our recover leak detection product. But Earth observation as a whole has a fantastically exciting part to play in meeting the immense challenges that we all know our planet faces. Like climate change. We've all seen the recent news around Valencia, for example, which is obviously very sad, with loss of life, which very much includes all of us across all the sectors that you might be working in: transportation, mining, dams, levees, insurance, all those types of areas. So anywhere where earth and infrastructure has the potential to be influenced by underlying soil moisture. Next slide. So just very briefly, the ASTERRA technology, our unique patented technology, was originally developed by our CTO, our founder, associated with NASA projects to detect water under the surface of Mars. And that technology now enables us to provide a highly cost-effective solution when applied to the Earth. A few years ago, there's probably a handful of satellites out there, but if those that go and research it, there are circa tens and thousands, hundreds being launched regularly, and it's projected that by 2030, I think the figure is there'll be around 60,000 satellites. So this is a fast evolving and changing future technology, which is here today now. And the challenge is to connect all that measurement potential and benefits and connect it to our real world engineering challenges. And that requires a change of culture. You've got to embrace the new. You've got to challenge the way that your current thinking and methodology and traditional ways of doing things are happening. Okay, moving on. So very briefly, just to, I want to sort of talk more about how we match this to engineering challenges, but very briefly to the context for SAR, which is a reminder stands for Side Aperture Radar. So the phrase SAR, often people jump immediately to think of INSAR, but INSAR is just one type aspect of SAR. We're here, and I am personally talking here about L-band SAR, and there's all forms of other optical and more picture-based type Earth observation tools as well, of course, and they all play their part. So INSAR typically relates to what we call X and C bands, and more on that on the next slide in a moment. But here we're showing why SAR generally, which is the red band indicated at the bottom of the slide here, is why it's so useful, because the vertical scale here is the ability to penetrate the Earth's atmosphere. So you can see SAR penetrates through that Earth's atmosphere very easily and down, and in some cases, as we're doing, beneath the Earth's surface. So it's not an optical passive type Earth observation. We're not taking a picture. This is active satellite, with the satellite itself acting as the sensor, picking up the backscatter from the projected microwaves that are sent down to the Earth and reflected back. And the key point here is that SAR is therefore great for Earth observation, and it really does. L-band particularly provides us with some unique capabilities. So next slide. Yeah. So the green diagram here on the left shows you simplistically the different bands that make up SAR. So you've got X and C there. They're the ones that are commonly used for INSAR. ASTERRA, we're experts and we use the longer L band. This provides the ability, because of its longer wavelength, to observe subsurface below the ground. INSAR provides a way to detect small ground movements. They take a series of many images regularly over time and then plot the trend and the vector of direction and so on. So therefore it's reactive. It's there once movement has taken place. The movement is detected, but only once it has occurred. L-band is proactive, because soil moisture buildup is that early warning of geotechnical failure. Poor drainage or excess soil moisture is a major contributory factor in 75%, I think the figures are, of geotechnical failures. So that's why L-band, it really matters. 2 or 3 images a year is sufficient to spot those initial problems and to monitor for seasonal trends going forward. So the key point here, it's proactive. Moving on. So here very simplistically, the shorter wavelengths, the X and the C bands here, they have associated with them less ability to penetrate vegetation or other obstructions such as perhaps weather. L-band matters because it provides that ability, regardless of the time of day, to penetrate, measure down beneath the surface. Typically 0.5 meter or so, depending on conditions, can be greater, down to 2 meter depth or even beyond in arid conditions. And importantly here, we are measuring through this backscatter the actual soil moisture, because we're measuring what is called the dielectric constant. And that just means we have the ability to potentially differentiate between, for example, different types of soil moisture, potable water, salt water, that type of thing. So it's highly useful if you're trying to monitor and pick up changes in habitats, saltwater intrusion perhaps, or to pick up drainage failures or drainage performance issues. And drainage issues are a key risk factor in geotechnics, and we can monitor your drainage from space here, which is amazing when you think about it. Okay, thank you. Next slide. So, as I said, ASTERRA, we're experts in L-band. We're actually the largest commercial consumers of L-band in the world. ASTERRA uses this expertise to detect and map soil moisture. That's beneath the ground, as I said. And the key benefits are that L-band means day or night makes no difference. It's 365, 24/7. Well, regardless of the weather conditions, we can penetrate through vegetation. We can see beneath pavements and asphalt, down below the ground. And because we're actually measuring this dielectric constant, it means we've got that potential to differentiate between different types of soil moisture as well as the actual parameter. And here we are at a high resolution. There are some sort of comparable solutions that might be looking at resolutions the size of a football field or something like that. But we're at a sort of a 6 meter by 3 meter pixel size. It does vary a bit, something like that. And that's really then allows you to look at a high enough resolution to apply to real world engineering problems. And it's cost effective at scale. The image here on the right is of Scotland. But just as an example, you can see that with the images that we take, which are roughly, say, 50 kilometers by 70 kilometers, it means all the assets within that rectangle can be accommodated within our analysis. So you can see how many assets you might be able to fit within that. And that's when it becomes really cost effective. There are some limitations. It's not magic. There can be issues with if you have concrete surfaces, standing water we reflect off. So looking at a lake, we can't help you there. And if it's rock or perhaps complex urban built up areas with tall buildings, all of those present some challenges. But we do review all the areas of interest, as we call them, and confirm what we can and can't do and be successful in terms of what we can provide for each individual project. Okay, moving on. So quickly, just to reiterate, we have three main offers, well, two main offers really, as ASTERRA. And what we're known for historically has been leak detection for water and wastewater utilities. And that's what we call a product solution we call Recover. And associated with Recover, for some customers, they want an asset management tool for their pipework network. And we call that Master Plan. So think of those two things together. But today, the focus here is to talk to you about the same underlying ability to detect and map soil moisture for earth and infrastructure and geotechnical assets, but we call, when we're applying it here, we call that EarthWorks, and that's the name of our product solution, EarthWorks. And this is applicable across a variety of sectors and globally applicable. So remember, satellites are not restricted by boundaries either. So theoretically, we can look here wherever we wish, wherever in the world you want to look. Okay, thank you. So this is the way that we look at our markets and face into them. So the ASTERRA EarthWorks solution can apply with broadly similar use cases often across a standard product to detect and map subsurface soil moisture. Applicable, for example, road and rail cuttings and embankments, but maybe also looking for early detection of seepage in dams, levees, or maybe tailings facilities, or perhaps looking at an airport or some other large property estate. And we're tending to segment our markets here in order to group them by customer type, really. The underlying product is essentially the same, and the underlying technology is essentially the same. It's where it can be applied wherever geotechnical assets, earth and assets are to be found, and where soil moisture might be an important parameter to be monitoring. Thank you. So when we're looking at dams and levees, what we're doing here is when we're looking at a dam, we have that ability to detect subsurface soil moisture, and that's really helpful because that can be indicative of seepage, which for those dam engineers amongst us, you'll know that seepage is a really important thing to understand. So if seepage starts to emerge in a dam or a levee structure, that can then lead ultimately to a piping failure and ultimately to a catastrophic failure of that dam or that levee. And because we're able to detect that beneath the surface, we can detect something long before it's visible at the surface or before perhaps there's any vegetative change that might be detectable either. So we're talking here about earthen structures though, so we can't really be, we're not helpful where there are concrete dam structures, other than sometimes at the shoulders they do have earthen or earthwork type connections at the shoulders, at the edges, which we can help monitor. And obviously surrounding areas to dams, landslips into reservoirs and so on, also key to be monitoring, and that can all be done with the same imagery here. But the key sort of value proposition, if you like, for dams is for the monitoring of seepage. So here are some points really around the value proposition, if you like, for earth and dams and levees. Often they don't have problems very often, but they're often highly critical structures because failure, when it does occur, can be very quick and can be catastrophic, and unfortunately can lead to loss of life, and the downstream communities are often, very adversely affected. So regular monitoring for build-ups, trends, or anomalies of soil moisture as a form of early warning is now possible using our type of tool set, using Earth observation. And that can assist then with the ongoing risk categorization and assessment of those structures and those assets. And often then we're not trying to solve a problem alone, we're just one data set that informed clients and engineers can then use and couple with impact and scenario assessments, for example, to work out what the impacts of failures are and what the likelihood of failures are. And you can contrast this type of approach with perhaps a more traditional way of doing it, where you rely upon scheduled occasional visual inspections, often involving deploying personnel into remote locations all around the world, can be an issue. So we're not saying those activities can or should be replaced. Often they're regulatory as well. But here you can follow up those activities in a much more focused way, and resources can be optimized, and you can work on a scheduled-based, condition-based assessment. Well, rather than being scheduled-based monitoring, you can move to a condition-based assessment, and therefore be much more optimized and efficient in your maintenance approach. Moving on. So here's just a snapshot of for those that wanted, excuse me, 1 second. For those that want a full end-to-end solution, we have a platform where you can view this EarthWorks soil moisture data on a platform application, cloud-based. For those that wish, you can just import that soil moisture map as a layer into your own GIS data set if you want. However, for those that require that total application, we can provide it here. The grids that you can see on the left-hand side there, the squares, we call those smart cells. Some of them in this example are red. That's where we've set a threshold, or you, the client, us, can set a user threshold. And where that value is exceeded, it gives you an alert or an alarm indicator for that particular square. That's an important sort of end-to-end process, workflow process, that you can work out where to send and deploy people with the follow-up tools. And importantly, these tools you can take out onto site, because we have the applications that have been developed so that you can use this on a mobile device, on your iPad or on your phone. And you can see all this, and you can target and tag the results of the field inspections, be they photographs, instrumentation results, other forms of documentation can all be tagged back to that square, so it's all in one place for everybody to see it again. See it all in one place, be it in the office or in the field. So the cell that's highlighted brings up a pop-up. You can see the changes in soil moisture, and you can see that developing over several months of monitoring perhaps. We can also report it in the way that you can pick up trends. So even though you might not have hit a threshold, you might be trending upwards in a way that you want to know about, and we can pick that up as an early trend. For dam structure, for example, that type of build-up of moisture can be indicative of that progressive seepage failure, and you can pick it up potentially in its very early stages. So slope failure or perhaps drainage performance issues, all of those are use cases where soil moisture build-up anomalies, patterns are all important or can be important. But here you have a decision assist tool where the case for follow-up inspection and actions are indicated. So what we call actionable insight, which is a buzzword, but that's what we're trying to provide here. And as I say, your field crews, we provide all the training required so that they can actually then use these tools in the field, so that all that information is kept in one place. Thank you. So Yoni will just get this to run. So this is just a very quick animation for a dam, just to show you the type of data set that you can see. So it provides here simplistically a heat map type view of soil moisture. So the red is where the higher soil moisture is, and obviously the green, the less. You can get an actual sort of banding for that, reported as you wish. I'm also showing here the squares overlain, which are preset as what we call these smart cells, so you can set alarms around that. Some of the engineers amongst you will look at that dam and think you can see about a third of the way up from the toe, sort of a diagonal line parallel with the crest. That's an interesting feature, probably well worth a follow-up. So not just looking at the smart cells, but you also get the data to look at the other sort of larger macro scale structures that might be of interest. So those that are familiar with GIS, you can turn all these layers on and off, just focus on the higher soil moisture areas, for example, and you can layer this in your own data sets and then combine it with other, perhaps drainage shape files, whatever it might be. So the smart cells here are typically used so that we can set, in conjunction with yourself, some thresholds. You as the customer can set them as you wish as well. It's all configurable, but it's all available on the one platform. They'll give you an idea of what the actual solution looks like in a sort of digestible way. Okay, next slide.
Thanks, Mark. I just want to give a note to everybody who joined recently. You're welcome to ask a question in the Q&A as the presentation progresses. You could drop it in the Q&A as it goes. I will address everything in the Q&A session that will happen after Mark's presentation.
Okay. Okay, so just still focusing on the dam use case, if you like. This is a piece of work that we did in Sweden called Loven Dam, which is obviously in Northern Europe, and therefore has cold weather and is got large amounts of snow cover through large amounts of through the year. Because of the that freeze-thaw cycle, that can lead to particular challenges with seepage occurring in some of these dam structures. So we were deployed to go and look for subsurface moisture that might be indicative of seepage issues. This particular project, the dam operator was asking us to look at this so they can compare with their other forms of data, sensor-based instrumentation, so check for correlation, if you like. So the satellite image we captured was back in November 23 now, so about a year ago. And perhaps surprisingly, if you think about it, but these were snow-covered, highly snow-covered, the whole area, but we were able to successfully penetrate that snow cover, mainly because it's really crisp and dry snow, and successfully reveal moisture within the dam structure below. And that really does illustrate the power of L-band. You wouldn't really be able to do this in any other way. And visual inspection, perhaps 9 months of the year, you would be able to get beneath the snow and see what's going on. So L-band really does provide a powerful answer here. So next slide. So the results here were really interesting. So you can see on that picture there how snowy we're talking about. This was a place that you had to be on a snowmobile to go visit. And several potential seepage areas were identified. Because where you do get seepage, there can be temperature differences. You can pick up and correlate where we were indicating an issue. You can see that from local changes in meltwater type evidence, which is to do with the temperature change of moving water versus static water, soil moisture. So the smart cells, which you can just see in that picture on the right with the red and the yellow squares, that was really highlighting where soil moisture was exceeding the preset thresholds. And really encouragingly, those results coincided exactly with the areas of higher temperature, and therefore the potential areas where there was some seepage taking place. So a really good result there. Moving on. So now just move to another sector. As I say, remember, same underlying technology. We're just applying this ability to detect soil moisture to anywhere where there's earthen or geotechnical infrastructure. So the big point for roads really is that if you've got a strategic road network or even a more densely urban network, for example, you can assess hundreds of kilometers of road network quickly and efficiently using Earth observation rather than going out and looking at small stretches at a time with field crews. So you're picking up potential issues, say cuttings or embankments that are susceptible to failures, or perhaps drainage is often a challenge. And when that drainage fails, if you can pick that up early enough, then drainage failures won't lead to further complications and more expense to solve afterwards. So we're picking up issues here that very often you wouldn't be visible to visual inspection. There might be surface vegetation, for example, that we would be able to indicate would be interesting to clear out the way and have a follow-up inspection in certain areas, and you wouldn't know where to do that without this type of tool. So moving on. So the points here really are that this is an additional data insight layer and tool for everybody. It really leads to the ability to better plan what you're doing, to better target your follow-up investigations. We're not trying to replace or change the way that you currently do things, but it be complementary to your current workflows, but just be more efficient and optimized. You could avoid, perhaps in some cases, unnecessary manual inspections at all. And for road and rail, for example, that can be a safety case, can be relevant here. You don't want people out close to carriages if you can avoid it, live traffic. And if mitigations need to be designed and constructed, maybe design new drainage or retaining walls, all those types of things, they can be much better informed and optimized in the design if you have this additional level of site-wide insight. And a point to mention here, I did mention earlier that increasingly climate change models, when added into traditional geotechnical asset models, they're showing the distinct acceleration in the deterioration timescales of those deterioration models of geotechnical assets. So interventions such as additional or better maintained drainage, as an example, can successfully extend an asset life cycle, which is a real return on investment case. And provided the monitoring is proactive and the actions are well targeted, you will get real benefits. So using these real data points, and remember we are providing real data points, and using a historic archive, you can sometimes provide historic data points, including that and inserting that into your current modeling can give you, using monthly or seasonal data, for example, it can really further refine your current models, take into account climate change, seasonal and annual changes and trends. And that helps you all present the case for additional budgets, perhaps, or resources that might be required, because we all know this is the challenges are accelerating when they're related to the climate change that we're experiencing. Thank you. So rail, in reality, there's a lot of crossover here in terms of the roads rail case. It's a similar use case in that we're looking at long linear or regional networks of assets with the potential for earthworks failures or drainage issues. So embankments, cuttings, those types of things. Sometimes I'm sat here today at the moment here in the UK. The rail assets in the UK are older, constructed when engineering standards were perhaps less understood. And so we have an issue with aging assets that are increasingly prone to problems. And this, geotechnical aging assets are an issue all around the world. Again, here in the UK, there's a recent article in the New Civil Engineer magazine, for those that read that. And that was quoting that despite additional focus and spend on monitoring by Network Rail here in the UK, they're still experiencing geotechnical failures and issues in areas which they hadn't expected in previously, unexpected areas. So they're kind of missing that 90% because they're only looking where there are known issues, where movement perhaps has already occurred. So that means they're still very much in that reactive approach, understandably perhaps, but if we were able to use a proactive soil moisture monitoring approach using our types of data insight tools, we would argue that you could get a better targeted follow-up and perhaps even head off some of those currently unexpected events before they happen. Moving on. So here, this is, if you like, some of the value statements and advantages that are applicable to rail, but they are quite similar to the road sector value proposition as well. So it really helps you identify, do that risk categorization and be proactive in terms of heading off damage or potential earthworks failures beforehand, and really optimize the way that you go around your monitoring and your maintenance and your site operations. Often if you're trying to assess where you'll want to spend your capital budgets, there might be an extent. There's an example I can think of here in the UK where we were monitoring a section where they had known problems, but our results showed a section of railway beyond that where there might be future problems. And so the civil engineering design solutions actually extended a bit further than originally planned in order to mitigate for the future as well as the known current. And obviously service interruptions are significant and costly. Even speed restrictions, when they're applied, are costly to business. So the impacts can be significant. And so, other ways of doing it don't really exist that you can do it in the same cost-effective way that we can do it here. Okay, thank you. So here, just a quick example. This was a retrospective exercise. So there was a rail derailment, unfortunately, in Scotland, here in the north of the UK. And it was clear, as is nearly always the case, that hidden moisture in the hillside or excess soil moisture was found to be a contributory or significant contributory cause to this landslide. So on the right hand side there, you can see this is a whole route, 66 kilometers of route corridor that we looked at for soil moisture on the west side of Scotland. And that was then, you could assess that and look and see if this is likely to happen in other areas of the route in the future. So it's a quick example really of how Earth observation can be used to monitor and assess a whole length of a rail network in a remote area here of Scotland, but anywhere in the world. It would have, I'd have much preferred, of course, it would have been better from our perspective, we would have been proactively monitoring before this occurred and gave an early warning of it, rather than being called in to react to a known issue and provide some additional information around what had already occurred. That's always useful, but I'd much prefer to be on the proactive side of things. But the journey towards proactive assessment for all of us is part of my message here today. My message regularly is convincing customers, clients, and engineers to move to that more proactive way of doing things and use this perhaps newly available data in order to help them do that. Okay, moving on. So if you can just run that. So this is just another example really of how this works this is a rail example for a Northern European city. You can see the corridors. We've masked out everything except the actual transportation corridors here. But this illustrates well how the smart cell grids provide a quick way of focusing. So the heat map view can be, it's a speckled view. What do you do with that? Where do you go? But with the smart grids, with alarm set, you can immediately see where you're getting red or yellow squares highlighted, and they give you a quick focus for the key areas to follow up on. And those thresholds can be set either for high or low soil moisture, but also to show up anomalies or trends from one image set to another. So from 1 month to 1 season or from year to year, and pick up those points. And of course, you can cross-lay this with other GIS data sets like drainage, for example. We often find good correlation between soil moisture build-ups and perhaps failures of under-track drainage for rail would be one good recent common example. Okay, moving on. So if you remember, we talked about these different sectors, and I'm going through them one by one, but really we are applying this technology wherever earthworks, geotechnical assets are relevant. And mining is an interesting sector for us because the mining sector is often in a remote area of the world. So alternatives to doing it other than Earth observation are challenging. or time consuming or expensive, all of those. And mines often involve a whole variety of different infrastructure. So as well as things like tailings dams, for example, which have significant impacts if they fail or have seepage issues. But there can also be broader status. These are large areas that require assessment, perhaps for environmental assessments, biodiversity, or other forms of environmental assessments where soil moisture can be interesting. Or they might have their own rail or road infrastructure contained within that set. We're really segmenting here, as I said at the beginning, around the client type, the customer type, rather than specifically different use cases. And you've got to remember, with that single image, that 50 kilometer by 70 kilometer image, or whatever it is that we're taking, depending on the satellite, that single image, we can assess soil moisture across all those different asset types. Whatever falls within that rectangle, we can do the assessment on for soil moisture, which can be relevant to all the different asset types that might be contained within it. Thank you. Next, moving on. So tailing dams can be particularly challenging asset to monitor. Many around the world lack clear ownership. Some of the older ones, they lack clear ownership, and that can hamper ownership of inspection regimes and so on. But often, even those which are orphan assets, if you like, the local municipalities still have a responsibility and require some form of risk assessment as part of their responsibilities to their local population and the local environment. So we can help provide that for them. But other more established mining companies, they often have, as part of their ESG, their social good governance, they need to be good stewards of their assets and the surrounding environments and demonstrate that they're doing that. And again, satellites are an ideal tool for that with Earth observation, and really ideal when you've got these remote locations and large areas. Okay, thank you. So moving on to the last category here that I'll talk about today, which is property. So property can be a little bit of a catch-all because there's a whole variety of customers that we'd put into this sort of customer segment type. But they might, for example, be large distribution warehouses, or perhaps regional airports, or perhaps supermarkets where there's many of them around the country, and they want a standardized way of and consistent way of monitoring them over a period of time, because that's the other big advantage here of this versus, say, manual inspections or visual inspections using typical deployment of engineers or inspection technicians. By using this type of Earth observation tool, you're getting a consistent set of data time and time again, and then therefore it gives you confidence in that the changes that you're seeing are real. So property really is a catch-all for any large estates that you might come across. So satellite observation comes into its own here then, where you've got that ability to look at large areas. That you've got to remember, other ways of monitoring at this sort of level of resolution across these large areas, it might not even really be possible to do it by alternative methods, and even it would be highly expensive to do it by manual methods, taking samples and taking them to a lab test or using field instruments. Even you still got to deploy a lot of resources to do that. And here we can assess large areas, large estates, regional estates, global estates in a consistent way, and do it once you get your imagery in and processed. It's pretty instant that you can see and focus on where you might be seeing problems starting to develop. So really cost effective when you're looking at these large property estates. Okay, so just to conclude here now, so as we said at the outset, ASTERRA proudly aligns itself and reports against the UN Sustainability Goals in terms of our impacts. And ASTERRA can help you and your companies, as well as reporting. We can report real tangible impacts against your goals, because Earth observation, satellite technology, these approaches are a great tool, and they have measurable impacts at regional, but also at a global planet level, if you want to do it that way. Another key point here, just to leave you with, is to remind you that Earth observation in general is here today. It's fast growing, fast moving technology. Is being increasingly recognized within governmental policy setting. And that's taking time to, understandably, to percolate down into day-to-day processes, but it is happening, and it's increasingly happening and accelerating. So it's time for us all engineers to look and embrace, consider the available technology, the available data sets and insights that are now around and that can be provided. So I just ask you to be open to the new. So thank you for your time. And I now, with Yoni's help, see if I can deal with any questions that may have been raised while I've been talking. Thank you.
Okay, thank you, Mark. We do have some questions already coming in. For those who have more questions, now is the time to drop them in the Q&A. We'll try to get through as much as we can. If we see that we're going over, we'll make sure to address the questions we didn't get to via email. Just some logistical ones to start. Imran asked about a copy of the presentation. Anyone who writes here that they want a copy of the presentation, we're happy to send it. You're also welcome to email the email address I dropped in the chat just a few minutes ago, inquiry@asterra.io, and we'll make sure to get you the presentation. A question from Alessandro about leaks and asphalt. Different product. I'm happy to address that separately via email. And I see another question about the leak detection product as well. We'll address those separately. Okay. First question from Nathan. Hi, what about soil moisture monitoring for agriculture?
Yeah, entirely possible. If you come across a use case for agriculture, it's not one we've tended to focus on. But it's where, if soil moisture is an issue, there is one particular inquiry that I'm involved with at the moment where people are trying to do system modeling, if you like, of a catchment area to consider where surface runoff might be occurring from, which can lead to issues from the application of fertilizers and other things. So I see a potential part there where we can be modeling the soil moisture on a seasonal change, and that can be incorporated into the models of that system catchment area. So yes, it is possible. If somebody wants to approach me with a particular opportunity, we can consider it, because we can look over large areas.
Okay, next question from Victor. What processing steps are necessary to go from a SAR image, such as the one we can download using GEE, that's Google Earth, to assessing soil moisture as done by the ASTERRA? Thank you.
Yeah, so that's really important. We've got, with our, although we're not here to talk about the recover leak detection side of the business, that's been running since 2016. So the point of that is we have a really mature process, quality assured process. So simplistically, from an initial inquiry, we will establish with you what we call an area of interest, which is essentially a polygon. Let's draw a line around the area that you're interested in, or if it's, for example, a road network, it would be the center line of the road plus a corridor either side, that type of thing. We then do an initial triage assessment of that area of interest to check that we will be able to give consistent and good results across the whole of that area of interest. Sometimes we can't. For example, if there's I don't know, maybe bridges that go over a railway or something, we won't be able to see through or underneath those bridges. So we would, if you like, cut those out of the result that we would provide. So once we've established that and everybody's happy, we then, in terms of the process, we don't own the satellites. So we have to make a request to task the satellite to take the image where we want to see it, that encompasses that area of interest I just discussed. And so that normally we ask for 2 to 3 weeks of forward-looking notice so that we can task ahead to do that. But once that image comes back in, we then have quite a, as I say, mature process where we quality assure the image that's been taken and run it through our proprietary algorithms and processes. and then we provide that as a data insight layer within the portal platform that I showed earlier on my slides. You get as a customer, you get a login to that for your area of interest, and then you can see the heat map and for the different images that you've ordered for different dates. And we can also then incorporate some other GIS layers sometimes, but you can access the GIS data yourself and then export that if you wish into other GIS data analysis if you're using more than one data set, and we're just one of them. So that's a repetitive process. Typically, it's a subscription-based model, so that people are, say, for example, taking images seasonally. So you may take 4 images a year so that you can plot from season to season and from year to year and pick up trends and anomalies associated with that. I hope that answers that.
Just going back to Alessandro's question, because I see it's also applicable for EarthWorks. Are we able to penetrate asphalt?
Yeah, so concrete, we can't, because without getting into technicalities, if you have a very smooth surface of concrete or you have rebar, the signal just gets bounced off it simplistically. But asphalt, beneath, we've successfully looked beneath railway tracks, ballast, successfully looked beneath asphalt pavements, those types of things. And just to cross-reference briefly to the recover product, which is the leak detection, we've had a continuous process there over many years with machine learning, as you can imagine. So we're now at a point where we've got a really high confidence level. And here, obviously, those pipe work is often beneath pavements and roads. We're well in excess of a 90% confidence level around what we provide as what we call a point of interest for that sector. So what I mean by that is, if you go dig here, you'll find a leak with over 90% confidence level. So that should give you a proof point there that this type of technology is applicable beneath asphalt. But there are some things we cannot see through. So rock, we can't deal with rock. We're looking at soil moisture that's contained within a soil matrix, if you like. So we're looking at earth, not rock. We can't see where there's standing water. So if it's a lake or a puddle, even a large puddle or a pond, we will effectively bounce off of that. So we can't help you there. So it's not a magic answer. It does have some limitations, but we'll go through all of that with you at an early stage to explain for your particular area of interest and your particular use case where we can provide with a level of, with good confidence and consistency.
Jorge asks, the penetration depth of the L-band is 0.5 to 2 meters. Isn't that too little when dealing with very robust infrastructures such as urban dams?
Short answer is no. So it does vary what depth we're actually penetrating to. And we can't be, just to be clear in terms of limitations, we can't tell you that particular result is coming from a particular depth. It does vary depending on the ground conditions. But the main point here to note, and I'll come on to the dam point separately in a second, but by getting 0.5 meter, 1 meter, 2 meters below the ground, you're getting into the seasonal story. It's not, you won't pick up increased soil moisture just because it rained last night. That would just, we're not picking up the results from having wet grass. We're looking at the underlying soil moisture, and that's what you don't have to go far into the ground if you've ever dug a hole before you get away from that top few inches of soil moisture that's to do with weather effects. If there's been a prolonged period leading to a rise in the groundwater table, that can be different. You do need to check that sometimes. But in general, by getting 0.5 meter and beyond, we're into the underlying soil moisture and the seasonal changes that are happening. And if something's happening that's anomalous to that, that's where we can begin to pick up that there might be an issue. So taking that across now to the seepage point around dams, the seepage dams are generally constructed of things which are not designed to leak, earthenworks. So the transmissivity, the speed of seepage through a dam structure is by definition or by design slow. It's not to say it's totally impermeable, but it's very slow. So if you're getting, say, 0.5 meter to 1 meter below the ground level, you might be several months ahead of that seepage actually emerging at the surface in any significant way that would be picked up by visual inspection, perhaps even more. So you can do analysis depending on your seepage analysis of your dam. But if you're seeing that far below the surface, half a meter, 1 meter, 2 meter, you're definitely getting months, maybe years ahead of when that would be picked up as a surface feature. So we are getting beyond that surface effect. We're looking at something that's more underlying, and that's where you can pick up the patterns, anomalies, and trends.
A question from John, which is a specific question about pricing, but maybe you can address pricing in general. Are you working yet on a per square kilometer cost model, or do I pay for the whole scene that I really do not need? I have 20 embankments where I only need the TSF embankment data on a monthly basis, not hundreds of kilometers of non-study area.
Sure. So we are tasking a satellite to take that image, and that scene or that image is the scale that we're talking about. So to be cost effective, the more assets or length of assets or number of assets you have within a single scene, the more cost effective it becomes per asset site location or per kilometer of railway or road or mile or whatever it might be. So the more you can fit in and analyze, the more cost effective it can be. We can still zone down and look at particular assets, but if you're looking at one small site, so just to give an example, real world example. So we've been asked to look at a rail project, and the way that's been designed, ideally what I'd like to be doing is to be proactively monitoring the whole of the rail route from one end to the other, and then being able to provide some insight into where issues could be arising, where they have already arisen, giving some additional insight into what's going on in those areas. But what tends to happen is, because the asset monitoring approach is reactive, they wait for something to happen, then they deploy and package that section up as a project, and then the project procures us to go and look at maybe 100-meter section of that railway. That's not cost effective, really, way of doing it. We can still do it, of course, but for that 100 meters, we could be looking at 20 kilometers of the same railway, probably for the similar price. So the process that we go through, and it does vary because sometimes we need more than one image for various technical reasons. For example, so we'll go through how often you want to have results, and what assessments need to go along with that. And then we will look at that area of interest, and then we will provide you with a subscription model to go along with that. And we do have some standard packages that then become relevant, which we call detect, advise, and what's the other one, Yanni? I've forgotten what the other one is. Anyway, but 3 stages. So prevent, there you go. Sorry about that. And then you can get to choose what you want from that. But we will, even a quotation proposal stage, we will process that initial assessment of the AII and how many assets and what you like to do. But yeah, you can look at it from the square kilometer range. We don't currently tend to process it that way, other than or consider it that way from a pricing point of view, other than sometimes for historic imagery, we will consider it that way.
Andre, yes, we do have webinars specifically about leak detection. We'll make sure to send you some links after we have many of those. Final question, because we're at the end of the hour, from Farnoosh. Do you have specialized software for monitoring soil moisture, and is it available to everyone for scientific use?
So we have patented algorithms and IP that allows us to convert this SAR data, L-band SAR data, into soil moisture mapping, detection and mapping. So to that extent is the software, the platform, that's what it provides and gives to you, which I've illustrated here. And as a customer, you can have a login into that. We don't tend to, because we're not here, as I mentioned, really, this isn't innovation. The tools are here. These are mature products now. It's about adoption. But for research purposes, if people want to reach out to me, I am can be interested in particular research topics, but it has to be a business case for us because we're busy trying to sell it as a real world product. But I don't rule it out, so please reach out if you have something specific in mind.
Okay, and on that note about reaching out, again, I've put the email address you could reach out to us on in the chat. That's inquiry@asterra.io. any other questions, comments, concerns, things you want to ask Mark, you're welcome to send to that email address. Otherwise, thank you everyone for joining. I really appreciate you all being here. Mark, thank you for your presentation.
Thank you, everybody.
We'll see you all next
appreciate
time.
the opportunity to talk to you all today. Thank you.
Thank you. Take care. Have a great day. Good evening.